What is going on, guys? Welcome back to another video on x86 assembly. So last time we talked about how to print hello world in x86 assembly, and we've seen that it's very complicated, mainly because assembly is the language of the CPU. So the CPU doesn't know what printing function does. It just knows how to transfer data between RAM and registers, and maybe even do some arithmetic operations. But that's it. We've seen that in NAND game, and now we're seeing the exact same thing inside x86 assembly. So this time, we're going to talk about how CPUs can call functions, because functions are very important in high-level languages. So it will be wise to know how to do that inside assembly as well. And just like before, the CPU actually has no idea what a function is. It only knows how to run instructions. So we kind of have to make the CPU go in the right direction in order for our function to work. And that's what I'm going to do in this video, which is to show you guys, using this Fibonacci example, how a CPU runs a function. So I've had this Fibonacci example up, and I'm using this very good website, which is asm.diveintosystems.org, and it kind of visualizes the stack for you. Because if I just program in the text editor, you guys probably won't know what's going on inside the CPU. This will actually show you, which is very, very cool. So shout out to them. I'll put the link in the description so you guys can check it out and play for yourselves. So now I kind of made this debugger execute this line right here already, and then we're almost about to execute this call Fibonacci procedure. So once again, we've seen this weird calling convention order where this time it again puts the parameter that we want to pass in. In this case, I said just call the first 10 Fibonacci numbers and print them out. It puts them into EDI. Why not EAX or EBX or any of the other things, for example? And that, of course, lies in this document right here. This is the System 5 Application Binary Interface for AMD 64, or just another term for x86 64. This document specifies the conventions for a lot of different things, but among those different things is parameter passing. And the reason why it does that is because if you don't have this, everybody will do their own thing. So I will write my program the way I want to. You might write the program the way you want to. Compilers won't be standardized, and it's just going to be a whole mess because your program won't run on my computer, and my computer won't know how to, again, address the stuff that you decided. So this standard was created so that it's just basically saying, everybody, we're just going to all agree on this convention. That way, it's going to save the time of everybody, and it's just going to make everyone's lives easier. Now, of course, in their infinite wisdom, Microsoft decided that Windows should follow a different calling convention, which is, again, the reason why stuff in Windows can't run on Linux, because it's just completely different. Oh, okay, maybe not completely, but even the parameter passing, there is subtle differences, and subtle differences mean a lot in assembly. So we're going to not talk about Microsoft and, again, what they've done to Windows. Just know it's different from Linux. That's the reason why, or I guess partly the reason why you can't run code from Microsoft and onto Linux. Okay, enough yapping about all of that. So we're going to actually follow through in the table of contents. Parameter passing is the one, so page 22, just click on that. This will show you the actual parameter passing. You got to scroll down a bit into this table, and this will explain why we've done the order that we did, which is the first argument is RDI, second one is RSI, the third one is RDX, fourth one is RCX, and then the fifth one is R8 and then R9. And then you might also wonder, what's with these register names? What's up with them? You went from RAX, RBX, RCX all the way to S, and then B again with the P, and then SI and DI, and the numbers. What's with this? Well, that's because x86 is a very old instruction set. It's probably almost half a century old at this point, and it has a lot of stuff put into it over the years through backwards compatibility. So that's why you just get this weird naming of registers. I will say ARM does a much better job at naming registers, because ARM starts at R0 and then just numbers it like you would intuitively. But again, x86 had to, for whatever reason, we ended up with this monstrosity of register naming conventions. So you just gotta deal with it if you want to program in x86. Otherwise, switch to ARM or some other instruction set. So you might also wonder why only 6. What's with the 7th or the 8th or the 9th argument? What happens if my function has like 20 arguments? What happens to them? Well, first, why 6? That's because usually functions stay within 6 arguments because otherwise you're just kind of making it a little bit bloated. But again, that's not really a good reason. So this actually deals with stuff that's above 6 arguments, and that will go into the call stack, which we'll see back here. So the 7th argument onwards will go into the call stack. But guess what? The call stack isn't just dealing with arguments greater than 7. It also deals with stuff like local variables, which is a very important concept in programming. It also deals with stuff like return values. So the call stack is how CPUs implement functions. If you take away nothing from this video, just know that the call stack is how functions are implemented inside assembly. So now this explains the reason why we move into EDI, mainly because we have that convention kind of telling us to do that. Now we're going to call this Fibonacci program, and this call is nothing but just a label. So this Fibonacci isn't a function, it's just a label up here pointing to this address, 401106. And keep that in mind because you'll see later on we have these addresses show up again, because again, the CPU doesn't know what Fibonacci means. It just sees it as addresses. We know Fibonacci because again, it's just good for us, but again, bad for the CPU. When we press next, it will call it. Notice how RIP, which I guess isn't shown here, but it jumps to this address. Now it'll start running instructions from this address, but it push something onto the stack. It pushed this value, 401164. What is this address? Well, this is the return address, because what happens when we're done calling Fibonacci? Well, we go to this instruction, and this instruction has the address 401164 in hex. That is important because if it doesn't push this, then the CPU won't know where to go back. It'll just continue running and then it'll just crash. That is why we need to push stuff onto the stack. The next thing it's going to push, so we're just going to continue, it's going to push the base pointer or the frame pointer. So the frame pointer establishes the local variables. So now you can see the frame pointer is pushed here, and then the stack pointer gets allocated again by moving the stack pointer to the base pointer. So when we press next, the base pointer and stack pointer meet up. And then now we know that this stack frame starts at this address. So that's what the frame pointer kind of establishes. It kind of establishes scope. So if you've ever heard scope inside programming, well, this is what scope actually is. Local scope, stuff like that, all of this, local variables, we'll see that next. So this instruction subtracts 16 from RSP. Now, why subtraction? Well, that's because the stack actually grows downwards, which means if you want to push stuff on the stack, you have to subtract. If you want to remove stuff, you add. So we're going to subtract 16 because we're going to allocate space for 16 bytes, and that all goes to local variables. So press next. You can see it allocates two 8-byte variables, and the stack pointer is now in this address. But notice that the frame pointer stays because the frame pointer needs to keep track of where we started so that at the end it knows where to return. Otherwise, again, the CPU won't know where to return. When we press next again, we will move EDI. Keep in mind, EDI was our parameter that we just passed in. And then we got to save EDI to this new space, this frame that we created, and it will save it to RBP -8. By the way, I know it's ugly AT&T syntax. Intel syntax does it much better. But this basically just says we take the contents of RBP and then we subtract it by 8 and then move it to that memory offset. That's why we see here, this value is 0xa, which is hex for decimal 10. Now, let's continue again. This compare instruction basically is an if statement. So again, we've talked about this in NAND game. If you've been following along with the series, we compare by subtracting, and then we jump based off of the result of the ALU instruction. So this basically just says, we'll jump to this label if it's greater than 0. Otherwise, we just continue and move on. So we're comparing 1 to this address here. So this instruction basically goes to the stack frame, RBP -8 offset. Oh, the value is 10. What's 1 minus 10? Well, actually it's 10 minus 1, it's always, I believe, the second operand minus the first one. So 10 minus 1 is 9, and 9 is greater than 0. So this instruction will jump. So when we press this, boom, jump all the way down here. We skip all of that mess. Actually, not that much, because you see this was jumping down here. But that just basically says, now we're going to move this back to EDI. So, because again, it's a recursive function, so we're preparing to call it again. Press next, and then we will subtract 1 to EDI, and then we will call Fibonacci again. And then the same thing happens again. When we call Fibonacci, saves the return address, moves the frame pointer up, and then creates a new stack frame, and then this runs all over again. Now, I'm just going to edit this code because there's 2,000 instructions, and actually, I might be able to jump to, like, for example, 1990. At this point, I don't know where we are right now. So, okay, I'm just going to edit this assembly code. Again, go to this diveinthesystem.org if you want to try it for yourself. But I'm just going to edit this, and I'm going to pass in just 1 instead of 10, because otherwise the recursive thing makes it forever to step 2. So I'm going to run this again. This time it should be way less. Yeah, only 24. So we're just going to step to, for example, let's say like 15. At this point, we're still inside this Fibonacci instruction here, this procedure. This time, I just want to show you what happens when we return a value. So now we're done. We are done with all the procedure calls. Again, I edited it to be 1, but just think of it a recursion going all the way down to 1. We're finally done with all those recursive calls. We're ready to go back to the main function. And let's see how that works. So first, we have to move this offset to EAX. Now, why EAX? Let's go back to the ABI. EAX is the first return register, which means return values get put into RAX. And by the way, the reason why it's called EAX is just because it's the lower 32 bits of RAX. So it's still RAX. It's just the subsection of RAX. Next thing we're going to do is EAX now has that value. We're going to add 16. So we're going to clean up the stack. This is where scope gets destroyed. So the stack pointer now goes back down here. You'll see it adding 16. And then it meets with the frame pointer. And all of these guys still remain, but for all intents and purposes, they're basically deleted. Because remember, CPUs don't actually delete stuff. They just mark stuff as being cleared. Now, we're going to pop RBP. Now, we are on this return address, this 164 I just talked about. This is down here somewhere, 164 right here. Watch this. Pop this. Boom. Now we're back to main. And then we can continue running until it finishes. So that hopefully just shows you how the stack kind of pushes stuff. When we're calling it, we're pushing the return address. And then finally, when we return, we go back to the address. And that's where the term return 0, return whatever comes from. Returning literally means return back to the function that calls it. And the stack frame helps accomplish that. So hopefully you enjoyed this video. Learn something about the stack frame and call stack and how procedures get called inside assembly. And stay tuned for the next one. I'll see you then.